Hello everyone, this is Shruti Saxena Das, and in today's lecture we are going to discuss about depth first search algorithm, which is traversing algorithm in a graph. So in the last lecture we have discussed about traversing in graphs. In that we discussed that we are having two algorithms. First one is breadth first search, which we have already discussed, and the second one is depth first search. So in breadth first search we were using queues, and uh, in that we were accessing nodes in breadth wise fashion. In this one, in depth first search, we are going to use stack, and we are going to traverse the nodes in depthward motion. So what we are going to do, so first of all, DFS traverse graph in depthward fashion. Okay, so depth wise it is going to access nodes. Traversing means that we have to visit each node at least once, at most once, not at least, at most once. And for traversing nodes in a graph we have two algorithms, BFS and DFS. In case of DFS, we are going to visit nodes in depth wise fashion. So here we are going to access it in depth wise fashion. Secondly, it uses stack. BFS was using queue for this purpose. Here we are going to use stack. Now this algorithm uses the idea of backtracking. Uses the idea of backtracking. Now what does it mean? Backtracking means that when you are moving forward and there are no more nodes along the current path, then you can move backward on the same path to find the nodes for traversing. Okay, so suppose you are having from A, you are moving towards B, and then you visited D. Now see, suppose graph is of this type, then from A you're going to access B. Now from B you'll access D. Now after D you're not having any more node. You have already accessed A. Then from A you access B, you have marked. Now when you access D, you visited D, you marked it, and then you're not having any more nodes after D. So again what you have to do, you have to do backtracking. You'll again go to B and check whether there are any neighbor nodes which are not visited yet. So here you are having C. So this is the case of backtracking, that in case of DFS, if you are not having any node, okay, along the current path, then you can move backward on the same path to find the nodes for traversing. Okay, so here the basic steps are, first step will be that you have to pick starting node. Pick starting node and push it on the stack. Okay, and then we have to check for the adjacent node for this particular node. And what we are going to do, mark starting node as visited and pop it from the stack and print it. Okay, and now the element or the node which you have popped, you have to check the adjacent node for those for that particular node. So what you are going to do in the second one, insert the nodes adjacent to the popped note. Okay, and then again you have to do this procedure again and again, that you have to pop a note from the stack, so to select the next node to visit, and you have to push all its adjacent nodes into the stack. You have to repeat this process until stack is empty. Okay, and every time you visit a node you have to mark it, otherwise same node may be visited more than once. Okay, so this is the procedure. We have to pick a starting node, like in this case, suppose you have picked A, you have to push it in on stack, you have to mark it as visited, and then you have to delete it from the stack, and you have to place the adjacent node to it. So in this case you have a direct edge to B, so we'll insert B, and then from B we have direct edge to C and D, we'll insert these nodes. So like that process will go on. So this is the basics. These are the basic steps of DFS. Now we are going to discuss the pseudocode, and then we'll discuss one example on this. So what will be the pseudocode for this? See, DFS will take two parameters. The first one is graph, whole graph, and the second is the source vertex, from where you have to start your traversing algorithm. Let capital S be the stack. Okay, this is the stack which we are going to use. This data structure we'll use for the traversing of a graph, and then in this S we'll push this starting vertex small x. Okay, small s. Now once you have pushed this particular node which you have received as a parameter for this algorithm, you have pushed this into the stack. I will mark this S as visited. Okay, and what we have to do, we have to continue this process until your stack is not empty. Please don't confuse between capital S and small s. Capital S is the stack and small s is the source vertex. This is the source vertex. Okay, so here we are talking about capital S. If stack is not empty, then what we have to do, we'll pop the element. Okay, we'll access the top element from the stack. So top element must be source vertex right now, so that will be stored in V, and then we'll pop this element and print it. And now the element which you have popped, for that element, for that particular node, we'll check the neighbors. So for all neighbors W of V in the graph, what we have to do, if W is not visited, if the neighbor is not visited, then simply push it in the stack. Push W in the stack and mark it as visited. So this is the pseudocode for DFS. Here we are receiving two parameters. The first one is graph, the second one is source vertex. And in DFS we take stack for implementation. So in a stack we are inserting source vertex and marking it as visited. If the stack is not empty, then you have to pop the topmost element, topmost node, and we have to check the neighbors for that particular node which you have popped. If any of the neighbor is not visited, then you have to push it on stack and you have to mark it as visited. This is the pseudocode for the DFS. Now we'll discuss the example on this. So we'll take one example. Here we are having A. Okay, so suppose this is the graph which is given. So what we have to do, we have to start with a stack. So we'll take one source vertex. Suppose we have taken A in this case. So what we are going to do, we'll take the stack. We'll insert the starting vertex, which is A. We'll mark it as visited. And then we are going to pop it and insert the neighbor element, neighbor node in this one. So after popping it, we are going to print it. So in the output, you are getting A. Okay. In the next step, this was the first step. In the second step, what will happen? We have deleted pop, we have popped A, and then what we have to do, we have to insert the next element, neighbor element of A. Now the neighbor element of A, if you can see, this one is the directed graph. The next one, from A we can only go to B, we cannot go to D as the direction is from D to A. So what will happen? The next element will be B. B will be inserted, and in the output still we are having A only. In the output array we are having A only. Now we have inserted B. We'll mark B as visited, and after that, in the third step, what we'll do, we'll pop this B, we'll print it, or we'll insert it in the print array, and then we'll insert the element which is the neighbor of this particular node. So neighbors are C and E. So we are going to insert C, and then we are going to insert E. So this will be the next step. After that, what we'll do, we have visited C and E. Now in the next element, again we are going to delete the topmost element. Now topmost element here is E. So what will happen? Here only C will be left, and we are going to delete E. We'll mark E as visited. We'll print it in output, and now only C is left in your stack. One more thing is there, when you are deleting E, then you have to check for the neighbor element. Now neighbor element, if you'll see, from E you can only access F. So we have to insert F over here. Now in the next step, what is the topmost element? Topmost element is F. So in this case, we have to delete F. And we have to check what are the neighbor elements, neighbor nodes of F. So if you can see, from F, we can only access B. But B is already visited. When B is already visited and there is no more node which we can visit, so what we have to do? We have to do backtracking. So in this case, see what happened. First of all, we visited F. We have deleted F. We have visited F and popped it. Now there is no more element which is not visited and which is the neighbor of F. So we have to do backtracking. Still you are having C in the stack. So we'll do backtracking. From here you'll go to E, then you'll go to B. All of these are visited. You can directly see the stack. So when you have deleted F, as there are no more elements to be inserted, because there are no more nodes which are adjacent to F, which we can access after F. So simply we have deleted and printed it, and now we are having C in the stack. So what we'll do after F, we are going to delete C. So what will be the next step? Next step will be that C will be deleted and printed in the output, and the neighbor of C will be inserted. Neighbor of C is, C will be visited, and neighbor of C is D. So D will be inserted over here. Next step, in the next step, D will be deleted and printed. So in the output, we'll be having A, B, E, F, C, D. So D is visited, and printed. And what will happen, we'll check for the neighbor of D. So if we'll see, from D we can access G, so G will be inserted. Now in this case, we'll visit G, we'll pop it, we'll print it, and we'll check for the neighbors of G. Now when you'll check for the neighbors of G, we are having F, we are having C, but both are visited, already visited and marked. So if when you'll delete G, again you are not having any more element which are present in the stack. So when you'll delete G, your stack will become empty. So when your stack will become empty, you have to stop this procedure, and whatever traversing you've got, that will be your answer. So this is the order in which you are going to traverse your graph. First of all, A will be traversed, then B, then E, then F, then C, D and G. You can see from A, B, then E. So in depth wise fashion we are going to visit these nodes. So that's why this is known as depth first algorithm, depth first search algorithm. I hope you must have understood. In case of any problem, any issues, you can write, you can post your queries in comment section. And in the next lecture, we are going to discuss Warshall's algorithm. Thank you so much.